Okay, my screen is visible, so I think we can start today's live session in the subject of design of reinforced concrete structures. So, can anybody confirm my screen is visible? Just raise the hand. So, okay, okay. So, yeah. So, hi everyone. Myself Umesh Vole. I am the PMRF research scholar at the Department of Civil Engineering, IIT Madras. So today I will be taking the subjects design of reinforced concrete structures live session. In that we will study the design of slabs. Okay. So again we can wait for some time, or we can discuss the basic things about the slabs till everyone will join, and we can move forward after that. So anyone know what is effective span? What is the effective span? What is a clear span? Okay, so clear span is directly it's given here in this figure. The clear span means the distance between the two clear distance between two supports. That's called as a clear span distance, and the center to center distance is called as this is noted as like this. But the effective span, what is the effective span? Okay, so the effective span is the distance we have to calculate by using the formulas, and that distance is significantly contributing to the moment and not the other distance. So that's why calculating the effective span is also important. Okay, so for the simplicity, for the simply supported beam, it can be considered as the center to center distance. And the effect, but for the different condition, the effective span of the member that is not built integrally with its support shall be taken the lesser of the following. Sorry, I have that the previous statement was not correct. So the effective span can be calculated as a clear span plus effective depth of slab or a beam. Okay, for the slab we will use slab, for the beam we will use beam. So the clear span plus effective depth and the center to center of support, whichever is the lesser, we have to consider that distance as the effective span, right? Okay, so not center to center. I told center to center directly distance as to take for simply supported beam, but that is not the case. By clause number 22.2 IS 456, this has to be taken care. Okay, so everyone know the little bit brush up on the UDL. W, small w is called as UDL, and the moment of the simply supported can be calculated as WL square by 8, and the shear force can be calculated as a WL square by 8 and the WL by 8. And if we consider the total load W, the capital W, and the capital W value is small w into L, then we can rewrite the bending moment as a WL by 2 and the W by 2 as the shear force. Okay. Okay, so let's move forward. So in this lecture we will study the first little bit theory behind the design of the slabs, and then different type of slabs, and then we will try to solve one problem, and then solve example we will see, and then we will see the one problem. So for the continuous beam and slab, as given here, if the width of support is less than the 1/12 of the clear span, width of the support is less than the 1/12 of the clear span, the effective span shall be as per the simply supported case. Okay, so for the continuous beam, if the width is very smaller, like 1/12 of the clear span, then we can directly consider it as a simply supported case. For the continuous beam or slab, for the end span with the one end fixed and other continued or intermediate support span, the effective span shall be clear span between supports. Okay, for intermediate span and for end span with the one end fixed and order is continuous. For there also the effective span shall be clear span between supports. Cantilever. The effective length of cantilever shall be taken as its length to the face of support and half the effective depth. So let me draw. Let's say this is cantilever. So what is there? It is a length, its length to the face of the support plus effective plus half the effective depth. So this distance plus, let's consider this is the d effective depth, then d by 2. So L plus d by 2 is the formula to calculate the effective depth for the cantilever, or the length to the center of support where it forms the end of a continuous beam. Here you can see. Okay, so the lesser of that we can consider it as the effective length of the cantilever. It will be clear in the upcoming examples. So for the frames it is very easy. In analysis of the continuous frame, center to center distance shall be used as the effective depth, effective span. So this is the effective span, right? So there is a way to solve the continuous beams. For that, if the substantially uniform distribution load over the 3 or more span which does not differ by more than 15% of the longest, let's say the UDL on this is not much varying and it is uniform, like it is the variation is less than 15%, then to calculate the moment and the shear force we can use the coefficient, moment coefficient and the shear force coefficient directly from the IS code. Okay, so to use that, span moments and support moments, different coefficients are there. So for the span moment near to the middle of the end span is 1 by 10. At the middle of the interior span, here middle of the interior span, it is 1 by 16. At the support next to end support, at the support next to end support, it is minus 1 by 10. At the other interior support, it is minus 1 by 12. And also for the shear, at the end support it is 0.4, and at the support next to the end support, here on the outer and inner faces, like considered here, this is considered as outer, this is considered as inner. For that 0.6 and 0.55 shear force coefficients are given, and at all other interior support is 0.5. Okay, yeah. So this is only a special case when the UDL is very much uniform and the change in the UDL is less, it must not more than 15%. So for moment at a support where two unequal span meets, or in case where the span are not equally loaded, the average of two values for the negative moment at the support may be taken for the design. Yes. So let's say this is our beam and here the span is less and here span is more. So for the negative moment design, we can consider the average of these two. Okay, so this is also done. So for the beam or the slab over a free end support where a member is built into the masonry, this is clauses for the masonry, and this is generally not much in use in our practice, but still we will see. Which develops only partial restraint. Member shall be designed to resist a negative moment at the face of the support of WL by by 24, where W is the total design load and L is the effective span. Such other resistance moment may be shown to be applicable. And beam and slab over a free end support where the member is built into the masonry wall which develops only a partial resistance. The shear coefficient at the end support given in table number 13 may be increased by 0.05. So this table number 13, this can be increased by 0.05. Okay. So when the masonry structures is given, so right, let's come to the directly to the types of slab, and we will see the design of slab from now. So what are the different type of slabs? Anyone? Like here it is straightforwardly given, but what is one-way slab, what is two-way slab, what is a flat slab, and what is a flat plates? Anybody want to answer, or at least try? Okay, so let's go. So the one-way slab is also it's called as one way, where they consider this figure. This is Ly and Lx. So the Ly by Lx is greater than 2, then it is considered as the one-way slab. Okay, and if it is less than 2, then it is considered as a two-way slab. So why it is called as one-way slab? Why it is called as two-way slab? So due to the action of its deflection, you see here in a one-way slab, a deflection of the slab is along the shorter span. So it is called as a one-way slab. Okay, and in two-way slab, deflection is along both the direction. So that's why it is called as two-way slab. Okay, and the flat slab is where the slab is continuous and it is supported on the this drop panels and on the column. So this is called as the flat slab, and this is called as a flat plate. Okay, so in this plan, which one is which one is one-way slab, which one is two-way slab? It's pretty much clear that this section looks like a one-way slab. This is two-way, this is also two-way, and all other are two-way. Okay, so loading on slab. So we should know some loading, how to calculate loading for the design of slab. So as per the IS 87/1997, self weight of the reinforced concrete is considered as a 25 kilonewton per meter cube, and finish and the partition generally considered as 1.5 kilonewton per square meter. This is square meter, this is a meter cube. Okay, and the characteristic imposed load for the roof with axis is considered as 1.5, without axis is considered as a 0.75 for the design purpose. For the floors, 2 kilonewton per square meter for the residential building it is considered, and 3 square kilometer is considered for office floor. Okay, yeah. So concrete cover, table number 16, clause 26.24, mild exposure, nominal concrete cover should not be less than 20 mm. However, for the main reinforcement up to 12 mm dia bar, for the mild exposure the nominal cover may be reduced by 5 mm. So when we use the smaller dia less than 12 mm, then we can reduce the nominal cover by 5 mm. That we will see in the solid exam. So the concrete cover is done, loading on the slab is done. Any questions on this slide? These values are directly taken from IS 875, so that we have to remember. Okay. Okay, let's go to the next slide. Yeah, for the serviceability criteria. So what is serviceability criteria? So till now we are looking for the collapse criteria, like when the beam will fail, what is the moment carrying capacity of the beam. But serviceability criteria is also important, where we will check how much deflection is allowed in any member, and the crack should not be there, because it will be very unpleasant for the occupant to stay there if their slab is already deflected. So it will be very uneasy to stay there, so people will not prefer to stay there, even if that is fully designed properly, and it will not like it is having enough strength. But if it is deflected, then serviceability criteria will not match. So the vertical deflection limit may be generally be assumed to be satisfied, provided that the span to depth ratio are not greater than the value obtained as given below. Basic values span to depth up to the 10-meter span should be 7 for the cantilever. Simply supported it is 20, and for the continuous it should not exceed 26. Okay, span by depth ratio. Okay, so it should not exceed that. If they exceed that, then there will be excess deflection. For the span about 10 mm, the basic values may be multiplied by 10 divided by span in a meter, except from the cantilever, in which case deflection calculation should be made. Yeah, so if that more than 10 meter is given, then also we can multiply by 10 divided by span in meters, whatever it is there, and by that we can calculate the new these numbers, and we should not exceed that. Okay, so control of deflection. The final deflection, this clause should be matched. The final deflection due to all the loads, including the effect of temperature, creep, shrinkage, and measure from the as cast level of the supports of the floor, roof, and all other horizontal members should not normally exceed span by 250. So considering everything, every load is coming onto the structure, deflection should not be greater than span by 250. And the one more clause, the deflection including the effect of temperature, creep, and shrinkage occurring after the erection of partitions and the application of finishing should not be normally exceed span by 350 or 20 mm, whichever is less. Okay, this is at the later stage, this is at the initial stage. Okay, yeah, let's move forward. So depending on the area of the stress of the steel for the tension reinforcement, the basic value shall be modified by the multiplying with the modifying factor obtained as a figure 4. This we will see in upcoming problem. And depending on the area of the compression reinforcement, the value of the span to depth ratio be further modified by multiplying with the modifying factor obtained as per figure 5. Okay, so modifying factor also we can change if there is a area of a compression reinforcement is given. For the flange beam, the basic value be modified as a figure 6, and the reinforcement percentage for use in figure 4 and 5 shall be used on the area of the section B and DF. So this is the reduction factor for the ratio of span to effective depth for the flange beam. For the flange beam, how the reduction factor is calculated, for that this figure is used. So let's see the one problem, and then we will apply all the formulas and try to understand one by one. So in this, the problem is design of one-way slab where a simply supported RCC slab for the roof, and their dimension is given as 3.5 meter to 8 meter inside dimension with 250 mm wall all around. Assume the live load to be 4 kg per meter square and the finished is to be considered as a 1 kg per meter square. Use the concrete M20 and the steel Fe415. Okay. The first step we will see is calculation of a factor loads. Okay. Before that, we will assume our span by D to be, let's say, considered as 25 to calculate what is the depth of slab. So we know the span, the shorter one we will consider because it is one-way slab. It is but obvious that because 8 by 3.5 is greater than 2. Okay. This one. So it's a one-way slab. So span we considered as a 3500 and the D is already we have considered span by D as 25, so we got the D as to be 140. So total depth we can calculate by considering clear cover to be 15 because we are taking 10 mm dia, right? If we take the dia less than 12 mm, then we can consider less cover, as we already seen here. Yeah. So for main reinforcement up to 12 mm dia for the mild exposure, the nominal cover may be reduced by 5 mm. So here 20 minus 5, they have considered as 15. So they have considered as a 15 here. See, 15 as a cover and the diameter, assume 10 mm dia bar. So to the center of the bar we will divide diameter by 2. So by addition of this, total depth D, capital D, will be 160. Okay. So dead load we will calculate. So for that, depth into what we will do, what is the unit weight of the reinforced concrete. So it is a 25, right? In the load we have studied, right? Here, see here, it is considered as 25 kN per meter cube. Okay, 25 kN per meter cube it is considered. So by multiplying that, we got slab dead load as a 4 kN per meter square and finisher it is given as a 1 kN per meter square. By adding that, total dead load becomes 5, and consider the live load to be at the maximum of 4 kN per meter square. That this is assumed value. Okay, you can consider 3 also, but 4 is the maximum possible, so we have considered the maximum as possible. The factored load is 1.5 into the addition of these two, so it becomes 13.5. Okay, so the factored load we got from here. Now the effective span we will see. So the clear span is 3.5 and our width is 0.25. So by adding that, it is become 3.75, but our D effective depth is 140 mm. So by adding that, it becomes 3.64. The lesser of this value we will consider as the effective span. So our effective span is 3.64. Why we want effective span? To calculate the bending moment, everything we require this. So total load per meter width, we can directly calculate that as bigger W is 13.5, where this is taken from here, and into 3.64, that's 49.14 directly is calculated. Okay, so this will be used again to calculate the moment here. So this big W we have already calculated, right? This is big W, which is small w into L. Okay, so we will directly use as formula we know mu is equal to W by 8 and V is equal to W by 2. That we have seen in the first slide. I will show you. See these formulas, right? WL by 8 and W by 2. So this is capital W. Or we can directly use WL square by 8 or WL by 2 when we use smaller W, which is a per meter. Okay. Any problem there till now? So we have used this two formula and we have calculated the moment and shear force. Okay. Any problem till now? Okay. So we can go ahead. So check for the bending. Sorry. As we know, for the Fe415 steel, the bending moment can be given as 0.138 FCK BD square, right? So the D will becomes like this, mu by 0.138 FCK B. We know all the values. By putting that, we got D around 90 mm, which is less than 140. So it's good. For that resisting the moment, only 90 is required, but we are providing 140, so our design is safe, right? E provided is 140 and D calculated is only 90, so it's good, right? Any problem in understanding this? 140 is coming from where? 140 is coming from here. Okay, so D we have calculated, D provided and D computed is also we know. Check for shear. Check for shear we can do shear force we know, B and D also we know. D it is taken as 140. This is only 0.1755. In the table number 19, and for the area of steel usually in the slab it is around 0.15%. For that, if you check, the tau C becomes 0.28. So tau V is less than tau C. So it's safe, right? So for the calculation of the steel area, this formula can be used. X by D is equal to 1 by 2 minus under root 1 by 2 square minus 6.6 mu by FCK BD square. So by putting all the values, X by D we can calculate, which is coming as 0.1685, which is less than 0.48. So good. And then we will calculate the lever arm. So lever arm can be calculated as D in bracket 1 minus 0.42 directly we can write, and X by D. So X by D we have calculated already here. That we have put here. So we got the lever arm to be 130. So AST directly formula we know, mu by 0.87 Fy and lever arm. So by putting that, we got the AST. So this for the spacing, it's easy to calculate spacing required, which is equal to 1000 into whatever the steel reinforcement you are providing, that area. So let's consider I am providing the 10 mm dia bar. So the area of the 10 mm dia bar is becomes 78.5 mm square. So 1000 into 78.5 that's area of the bar divided by the whatever the area we calculated, which is required to register all the bending moment, which is 478.6. By dividing that we will get the spacing. Okay, so this is the 165 is the spacing. So we can provide lesser spacing for the more safety purpose. So one question from sir, will the student be allowed to use the design codes in NPTEL exams? So if the question is asked where the design code tables are required, then you will be provided with the printouts of only that portion, not whole IS code. Okay, so this is not fixed always. Sometimes they will ask some question where there is a requirement of IS code, some pages of IS code, so they will provide you that in the exam center. But if the questions are not from the not required in IS code, then they will not provide. So the basics formula you should remember for the calculation of bending moment and area of steel. Okay, the basic you should know, because always it is not fixed. Okay, so we will go ahead. So by doing that we provided at the 150 mm center to center distance. Okay, so by so our spacing was 165, but we given the spacing has to be 150. So our AST becomes 523. You can calculate that. So the AST provided will be extra. We have provided whatever we calculated, from that we have provided extra because we reduce the spacing, right? So whatever we calculating we are calculating for a 1 meter span. So AST provided is 523, AST required is 475. So the modification factor we can calculate, where this is the formula is given here, which is equal to, here it is also given, Fs is equal to 0.5 into Fy, and which is like the cross section area of which is required and which is provided. Okay, so this we have put here, this is required we got, and whatever the provided we provided extra means like it is conservative approach, it's safe. Okay, so the Fs we calculated from here is 218. So 218 is between, here we have to see 190 and 240. So this line around we will see, and the percentage of the steel we calculated here for 523, which is coming to be 0.37. so around 0.4 we will see it here, and between these two, between this here we will come. So it will come less than 0.66. so the professor have taken as modification factor as 1.55. so the L by D calculated will be modified by 1.55, so it is coming as 31. Assume L by D was 25, which is less than whatever we calculated. So the assumed was okay to go because we have gone for the conservative approach. Okay, so D if we calculate by whatever the L by D we got, from that the D is coming to be 117, but what we have provided 140, right? Depth at the starting we have provided 140. So it is okay. It is okay means it is extra safe, it is uneconomical, you can say. To we have to redo this to get to the actual answer, but that is not necessary. Now in the NPTEL lecture they will not ask these big questions, but in that they will ask the smaller questions like what is the reduction factor. So for the reduction factor you should know this formula. Okay, directly they will ask this formula into the ABCD, and the different formulas will be there, and you will get confused. This 0.58 they will change. So remembering this small formula will also help to get the good score. Okay, so secondary reinforcement, why secondary reinforcement is required? Anybody knows? Now the primary reinforcement we already provided for resisting the loads, everything is done. To resist the tension also, to resist the tension we provided the steel. Now we are providing secondary steel, which is the always secondary steel is above the primary steel, right? So secondary steel is provided to resist the cracks which are formed by the thermal due to temperature. If the cracks are forming, so to resist that we always give 0.12% of the steel. Okay, so 0.12% of the area, which is 1000 into 160 is the total length, b into this is a big D. Okay, this is not a smaller D, so that's why it is not 140, is the total from here. So this is a small d, this is small d, so the big D is 160 here, you can see. Okay, so this big D we have to use here, and then our area becomes 192, and we can provide 8 mm dia, and our area for the 8 mm is 50 mm. So the spacing we can calculate by the same formula, 1000 into area of one steel bar divided by total area. So our spacing becomes 260. So but there is a check for this spacing, is it correct or wrong? Okay, so for that clause number 26.3.3 is given, so it should be. So now the main questions are like that. So they will ask for the secondary reinforcement, what is the clause to check the spacing. So the option will be like this: 3D or 300 mm, 3D or 450 mm, or greater than 5 not should be greater than 5D or 450 mm. So this type of permutation combination option will come, and then we have to, then you guys have to choose the one answer. So remembering this also will help. So for the secondary reinforcement, it should not be greater than 3D or 300 mm, whichever is less, and also 5D and 450, whichever is less. Okay, so our spacing is 260, so which is less than 300 mm, so it's good. So we can provide a 250 mm center to center spacing for the distribution steel. So this figure, understanding this figure is very important. Okay, so these are the supports, this is the main slab. Okay, and the downward whatever you are seeing here, which is coming like this, and at the corner we will bend up this, because we don't require it here, because the tension here is less and the shear is more. So by doing the bent up we will get the extra shear capacity. Okay, so this bar which is also coming like this, it's bent up here. Okay, so these are the main reinforcement, primary reinforcement, you can see it here. This is the primary reinforcement, this is also primary reinforcement. Okay, these are coming at the down. So these dots are the secondary reinforcement. So and this secondary reinforcement is like this is this. Okay, all right. And primary reinforcement we already have calculated, which is having 10 bar and 150 center to center, which is given here. Okay. Yes. So any problem in this figure? And this is the section of, yes, any problem?
Sir, secondary steel is called distribution bars.
Yes, distribution is called as a distribution bars. Yes, correct, it is called as a distribution bar. And yeah, as I said, this bent up bar we will do here. So this is has to be done at the distance of 0.1 lx. So lx can be calculated as a 3500 plus 250, which is the w uh, width of the wall. So we will consider this as a lx and we will calculate this. Okay.
Okay, sir.
Yeah. And this section is like when we cut like this. So at that time, now tell me which one is at the primary and which one is at the secondary reinforcement. First of all, we have cut like this. Now I am cutting like this. Okay. So now it will become it will be same, like primary will be at the bottom only, but it will look like a dot dot. Okay, right? So the primary will be always at the bottom and the secondary will be at the above that, and this will be the distribution steel. But here it is vice versa, these dot dots are the distribution steel and this one is primary. Okay. So it's clear.
Yes.
Okay. So professor have also explained that when there is a case for the concentrated load, how to solve that problem. So let's consider if this is the concentrated load of the due to tire of uh, any vehicle. This can be distributed like this into the roads. So let's consider this as a varying coat and this is the total depth. So this will be the different layers of the road. So for the consideration of the distribution of load here, we have to calculate the value of this BE. Okay. So this BE we can calculate by this formula kx in bracket 1 minus x by LA into plus A, which is, and this k value is in the table number 14 of IS 456, and this A and this X, this this is the BE. So in the normal case we considered B as 1000 and we will design, right? For the every 1 meter we will design, but for the concentrated load this BE we have to calculate, which will not be 1000. For that this formula we have to use. Okay. This was a little complicated. I will say any solved example on this and then it will be clear. These A values are calculated for the different depths. We can calculate A value at this depth also or this depth also. When we calculate at this depth, the concentrated load will be at the higher intensity. When we calculate it at this depth, so the length is larger, so it will distribute and the intensity will be lower. Okay. Yeah. So we will see one problem and sorry, we will see one problem. Up to we will only say up to the design of the steel, and then we will wind up today's lecture. So the one-way slab problem is like design a simply supported roof slab for the room 8 meter into 3.5 meter clear span in size. If superimposed load is given directly to be 5 kN per meter square, and the use of M25 and the Fe415 grade is recommended. So for that we have to design the slab. So we will recall our steps, what we are doing. We are assuming span by D, some span by B we are assuming, then we are calculating the D. Okay, then we can calculate the large D also by considering some reinforcement, some diameter of the reinforcement. Then we can calculate the dead load also, the factor loads also. Then effective span we have to calculate the lesser of these two. In effect, after the effective span, this is used to calculate the bending moment. So this is used here. This is effective span is used for calculating bending moments and shear force. Then the required depth we will calculate by using this formula. Okay, and then we will check whatever the assumed value of the our depth of the slab, and whatever the computed should be always less than whatever we assume. So always try to assume a value of the slab between 150 mm. Okay, around 150 mm we can assume. Then we have checked for the shear, and then we have calculated x by d. X by d is used to calculate AST here. X by d is used to calculate a lever arm. Then the lever arm is used to calculate AST. Okay, there are the different formulas also to directly calculate AST, but it's required quadratic equations. That also you can directly use where some formula like plus minus under root b square minus 4ac by 2a, something like that type of formula is also available. That also you can directly use for calculating AST. Okay, and then this is not required. We will not go this far. We will only see till design of the main reinforcement in the last problem. Try to solve by assuming whatever you guys assume. This exercise is only to check are you guys remembering the some formulas, and are you guys are comfortable in solving the problem. So the solving problem will help to remembering some formulas which they will ask in the exams. Okay, I will give you some 3-4 minutes, then we will see the answer. Okay, shall we go towards the answer? Okay, let's see the answer and then we'll try to understand. So in this L by B always we will check first, which is greater than 2. So it's but obvious that it is the one-way slab, so we will consider a 1 meter strip. for the design purpose. And then we will calculate the D by considering some value of L by D. Okay, this is L by D. This is another formula they have used, but by considering the L by D as 12T, we can calculate the value of depth of the slab to be 175. The total D we can also calculate by considering, let's say, 15 mm cover plus 10 mm dia. So 10 by 2 is 5. So 175 plus 20, 195. Yeah. So what they have considered, they have not considered anything, they have directly calculated D, but the actual D will be 195. Okay, or sorry, it is 180, 190, yeah, 195. Okay, that's correct. So the, yeah, just consider like for the calculation purpose, if they have calculated as a 190 mm, for the dead load also they have considered 0.19, we will consider 0.195 into 1 into 25 is always same. For the dead load, superimposed loads is directly given as a 5 that we have considered here, but addition of these two is here. We have to consider factored loads, right? Factored loads we have considered by multiplying 1.5 for the better for the safety factor, that is coming to be 14.63. The maximum bending moment at the center is given by WL square by 2 because we are considering it is a simply supported slab, right? So our D, okay, so the after that what we have to see, sorry, after that we have to see, okay, in this they have assumed the support width to be 250 and assume the steel dia to be 10. Yeah, that I have also selected then clear cover and is 50, and then by, okay, that's why they are wrong here. See here, they have done the mistake. So if we are considering our example as 195 here, so it will become 175 again, and this 175 and this 175 will match. Okay, so our D is 175. So we will consider center to center distance between support plus width of the wall. So this is become as 370 or 3.75 meter, and when we clear span plus effective depth becomes 3.675. It will become 3.675 because our thing is not 19, it is 195 mm. Okay. Okay, so now we come towards calculating maximum bending moment. So we know 14.63 is our load and L square by 8. By doing that, we calculated the maximum bending moment. So now we have to calculate the D required, right? So for that the formula we use as 0.138 FCK BD square. They have written sigma CK. We know that we can write it as FCK also. So by rearranging the D for the calculation of D, we got the D to be 85 mm, which is less than whatever we adopted. We adopted D as to 175. 175 we adopted here. 175 we have adopted, and the required is only 85. So our design is good, but our design is very highly conservative, and it might not be economical. So in this question they have adopted D as 100 because calculated is 85. Let's say a little bit more, so it's 100. So again considering the clear cover as 15 and the radius of the bar is 5, and then the total D is coming to be 120. So the area of tension of steel is given as M by this formula. By putting and this is the formula where the quadratic equation has to be solved, and then we will calculate the area of steel. So this is the area of steel we got, and then the number of bars and the spacing we can calculate it by the formula 1000 into, let's say, diameter of one bar we have considered as 10 mm, then it will the area of that bar becomes 78.5 divided by total area. Total area is what? 785. Okay, 785. So by dividing that, it is clear that will become, will get 100 mm. Okay, so here also they got the center to center distance directly, but they have calculated by different formula. We already know this formula, so by this formula we got the 100 mm as a spacing center to center. But now we have to check for the maximum allowable. So it is 3D, and the 3D is 300, but our given is 100, so it's okay, and it should be less than 300 also, so it's good. So the provided bar 10 mm at the 100 of center to center distance is okay to give, right? Now we have to see for secondary reinforcement. Secondary reinforcement we already know we give 0.2%. So directly, but there we consider the total D, not small d. This is the larger D, capital D, not small d. Okay, so this D is coming here. Okay, so the area of the secondary reinforcement we got it here, and then again by this formula we can calculate the spacing, right? By doing that, the spacing come to be 333.33, which is greater than 300, so we can't use this. So we have to go for the smaller spacing, so smaller spacing is 300 mm. So we can provide 8 mm bars in this clear spacing between 300 center to center, so it will be okay for the secondary reinforcement also, and the primary reinforcement we have already provided here 100 mm. And after this we can check for the all the shear, deflection and all. That part I have not covered here, but we can do that also. Any questions in this? This is directly coming from IS code, 0.12%. For the secondary reinforcement, try to remember that directly question can come. What is the percentage area given for the slab in the secondary reinforcement? So directly answer is 0.12%. Okay, actually I don't have the assignment questions, so I don't know which type of questions they will ask in the final exam. So according to me, there will be multiple choices questions, and we have to select from ABCD. That type of question will be there, and the one or two question which can they directly ask for the design, so that you have to write by hand. Okay, so that nobody knows how they decide. So in that case you will be provided with the paper and some xerox of IS code pages, and then you have to solve the problem. So no worries, in that xerox all the formulas will be given which is required to solve the paper. So formulas you don't worry about, only the basic formula you have to remember. Okay, any question? So can we wind up for the today? and we can meet on the next week.
Sir,
Yes.
uh, few doubts.
Yes, yes, please. You,
Beams, design of beams.
in design of beam you have doubt.
Sir.
Okay, what is the doubt? It,
Okay, sir. For designing of singly reinforced sections in working stress method,
okay.
why we are take strain is proportional to the distance from the neutral axis.
Okay, strain is proportional to.
Strain is proportional to the distance from the neutral axis. Why we
Okay.
are take this statement, sir? Can you explain?
This is directly question. Can you in the assignment?
Yes, sir. We are calculating the depth of the neutral axis
Mm-hmm.
in two ways.
Mm-hmm.
To given the dimensions and reinforcement is given.
Mm-hmm.
We have one formula
Yeah.
and uh, stresses are given in the beam sections. Then
Okay.
calculating the n equal to n by n 1 plus sigma st by small n into sigma cdc. That's the formula. So,
So your question is from the neutral axis why it is proportional. Proportional.
uh,
So
uh,
strain.
strain is proportional to the distance from the neutral axis.
Yeah.
Why
So
we are
it is a triangle, no? When we calculate the uh,
yes sir yes.
yeah, strain block also and stress block. So we
Yes.
have not considered there in a stress block. We are not considering there as a parabolic, I guess. And in the strain also, it is like straight line. So I think the problem is coming from similarity of the triangles, and uh, we solve for the different depths. What are the different strains are coming, right? So it is proportional to the distance. So from there you are asking, like I will draw here. It is like this, right?
Yes sir.
Yeah. So
No, yes sir. Yes.
if at this level, if you want to calculate the what is the stress, so this can be calculated by similarity of triangles by if you know this distance and this distance, right? Neutral axis and this distance, if you know, then and also you know this as a 0.0035, right?
Yes, sir.
Okay, so we have to calculate this. So by if you know this and this, and if you know this
Sir,
also, so
this
calculate.
is limit state method, sir. Sir, wait. This is limit state method, sir. I am asking working stress method, sir.
Okay,
I'm
okay,
asking working stress method.
okay. So for the working stress, I will relook and I will let you know in the next class.
Okay, sure, sir. Sir, another doubt, sir.
Okay.
In the design of beam sections, why we are taking the bending moment equal to moment of resistance.
Yes.
Why we are take, sir? Can you explain it, sir?
So you consider that we want to resist whatever the bending coming on onto our beam. So the resistance provided by the beam should at least be equal to whatever the coming onto the beam. So if it is more the MR, the moment of resistance, if it is more, it is always good. But it should be at least equal to that level, so our beam will be safer inside. That's why it should be equal or greater than. So MR should be always greater than whatever the bending coming onto the our beam. So
Okay, for the safety purpose, we are
yeah,
taking
yes,
equal to the bending moment equal to moment of
yes,
resistance.
yes, and by that we can solve the problems also uh,
That's
by equating it. Okay, so but it will, if it is greater, it's always good.
okay. Thank you, sir.
Okay, so I will relook for the working stress method and I will let you know. Okay.
Okay, okay, thank
Okay.
you, sir.
Okay, bye. Thank you.
Thank you, sir.